So this section is on comets and asteroids. This is a picture of comet Hale-Bopp. It was one of the most attractive and easily visible comets of the 20th century. It showed up in March of 1997. It was really beautiful. If you found a dark sky somewhere, you could just naked eye see it. It was really fun. You don't see comets like that maybe once in a lifetime. My daughter was born in 96, and so I took her outside when she was 6 months old and pointed her head at it a few times so I could tell her that she saw it. But it was really pretty. So you see, we'll talk a little bit about comets in this. Comets typically have two tails, not always, but typically. One of them, this blue one up here, is called the gas tail or the ion tail, and this one's called the dust tail. And they're both, the ion tail is created by the solar wind blowing on the comet, and the dust tail is sort of made by the radiation. We'll talk about that as we go. So there are two types of small objects in the solar system, asteroids and comets. Just as there are two types of large objects, the planets, we have terrestrial planets and we have Jovian planets. We also have two types of small objects, asteroids and comets. And just like with the planets, the asteroids are the inner solar system group and the comets are the outer solar system group. That's kind of where the similarity to the planets ends, but asteroids are created in the inner solar system, inside the orbit of Jupiter, and comets are kind of outside that, and so that's why their chemistry is different, the same way the planet's chemistry is different. Asteroids are rocky objects from the inner solar system. Asteroids are primarily found between the orbits of Mars and Jupiter, but they can be found everywhere. The solar system is very messy, and so there's all kinds of stuff all over the place. Comets are icy objects from the outer solar system. Comets are typically, but not always, found beyond the orbit of Neptune, and they're sometimes called trans-Neptunian objects. Sometimes they're called Kuiper Belt objects, sometimes they're called Oort cloud objects, but generally we just call them comets. So first we'll talk about asteroids, then we'll talk about comets. So looking for planets and finding asteroids. So if you look at this table here, you'll see the list of the planets. And then in the next column, we have the distance of each planet from the sun in astronomical units. Remember, an astronomical unit is how far the Earth is from the sun. So the Earth is 1 astronomical unit from the sun. Venus is closer, it's 0.7. Mercury is 0.4, and so on. And so, Neptune is 30 astronomical units from the sun. The right column is take the number of the distance your planet is and divide it by the one that's 1 closer. So 0.7 divided by 0.4 is about 1.8. 1.0 divided by 0.7 is about 1.4. 1.5 divided by 1 is 1.5, and so on. Astronomers were looking at this maybe 100 years ago, 150 years ago, and noticed that, or maybe even longer, and noticed that that this number from Mars to Jupiter seemed to look like there was a gap. All of a sudden, this number, whereas for everybody else it's 2 or less, this number is 3.3, and so astronomers started looking between Jupiter and Mars for objects besides, for other planets. And what they found instead was asteroids. Ceres had been found by 1801, but by 1900 they had found 300 asteroids, objects between the orbits of Jupiter and Mars. The total, we'll talk about this in a minute, the total mass of asteroids is actually about 3% of the mass of the moon. We'll get to that. So this is a picture. The outer circle is the orbit of Jupiter, and the next inner circle, the blue circle, is Mars's orbit, and inside there is Earth's orbit. And so you can see these dots. These white dots are the asteroid belt, the thing we typically call the asteroid belt. There are asteroids scattered all over the place here and inside too, if you look carefully. I wonder if I can click on there. So you can see asteroids inside the Earth's orbit all over the place, right? So this is a computer-generated diagram, and it shows the positions of the asteroids known in 2006. If the asteroids' sizes were drawn to scale, correctly scale, none of the dots would be visible. They would be too tiny to be seen. Here the asteroid dots are too big and give the false impression of how crowded the asteroid belt would look if you were in it. This is commonly done in science fiction movies. The asteroid belt is very sparse, very, very, very sparse. When we send a probe to Jupiter, we don't worry about running into anything in the asteroid belt. We just fly right through it like there's nothing there. Um, you'll see a few clumps right on Jupiter's orbit. These are called Lagrange points. They're stable points for asteroids to be orbiting. And so they go around this Greeks group of asteroids go around ahead of Jupiter, and the Trojans lag behind. They're both about 60 degrees off. And those are stable spots in the orbits. We talk about that, why the gravity works for that in advanced physics classes sometimes. So some asteroid facts. There are fewer than 2 million asteroids of size larger than 1 kilometer, half a mile roughly, in diameter in the asteroid belt. It's hard to keep track of the ones that are a lot smaller than that because they're hard to see. The average distance between these asteroids is about 500,000 miles. So for an object that's half a mile in diameter, they're 500,000 miles apart. That's twice the distance to the moon. They're really spread out. The periods of these are in the range of 3 to 6 years. Their distance from the sun is about 2.5 to 3.5 astronomical units. Remember, Mars is about 1.5. Jupiter's about 5. So they're in the middle somewhere in there. This isn't quite right. There we go. That should say 500,000 miles there. Typical distance between them is about 500,000 miles. So they're very far apart. Even though rock has a typical density of 3 grams per cubic centimeter and asteroids are made of rocks, they tend to have lower average densities because they have space in them. They're often described as bags of gravel. They're just stuff that accumulated together and glommed on. They're small enough in size, that they don't get compressed the way something as big as a planet does on the inside. We get crunched because of the enormous gravity that a planet has. If it's smaller than 1 meter across, we call it a meteoroid rather than an asteroid. Anything that's smaller than a meter is like a space rock. Anything that's smaller than a meter in diameter is a space rock, and those we call meteoroids. There's a little jargon with this as well. A rock in space is called a meteoroid. One that enters the atmosphere is called a meteor, as opposed to a meteoroid. If it's in the atmosphere, it's a meteor. That's what a shooting star is. Shooting stars are meteors. One that makes it all the way to the ground before completely burning up is a meteorite. So you have a meteoroid, a meteor, and a meteorite. Shooting stars are meteors, and a typical one is the size of a grain of sand, kind of shooting star that you might see or try to make a wish on. Is very tiny. Oops. Oh, how about that? That's better. So the largest asteroid is Ceres, which is about 600 miles in diameter. Its mass is about 1.2% of the mass of the moon. So it's very small in mass. The moon's diameter is about 2,000 miles. It's the same mass ratio to the moon as the moon is to the Earth. And so you can kind of see why we might not want to make this a planet. Right? Ceres is considered a dwarf planet. It's the only asteroid so considered. The other ones are. Vesta is close to being considered a dwarf planet. A dwarf planet is a celestial body that orbits the sun, has enough mass to assume a nearly round shape. So if you're really small, your gravity isn't going to make you round. But as you get bigger and bigger, gravity is going to kind of make you round. It's just the way gravity works. It tends to make things that are sticking way out fall over and fall towards the center. And so when gravity is a dominant force on something, they tend to be round. Also, a dwarf planet has not cleared out the neighborhood around its orbit and is not a moon. In order to be a planet, you have to kind of clear out your orbit, and that's kind of what Pluto got Pluto kicked out of the club. Pluto is surrounded by lots of other stuff, and its gravity isn't strong enough to sort of clear out its orbit. All the rest of the planets did. Ceres contains about 1/3 of the total mass of the asteroid belt. So the main asteroid belt is only about 3% the mass of the moon. That tells you how little mass there is out there, and it's an enormous area. The acceleration on gravity is g equals 0.27 meters per second squared. If you remember, on Earth, it's about 10. So it's about 40 g's smaller, 40 times smaller than Earth's gravity. So if you can jump 1 foot vertically on Earth, you can jump 40 feet on Ceres. I would have mad ups on Ceres. I could be a great basketball player. So asteroids are typically categorized into 3 types, kind of based on their chemistry. C-type are carbonaceous asteroids, and that means they have a lot of carbon in them. S-types are silicates. Sometimes they're called stony asteroids. They have silicon. They're more silicon-based than carbon-based. And then there's an M-type, which are really metallic. The metallic ones are probably parts of asteroids that were chemically differentiated. In other words, when we talked about the Earth, chemically differentiated means the heavy stuff, the metals fell to the middle, and the lighter stuff floated on the outside. The Earth is chemically differentiated. All the planets are chemically differentiated. Some of the asteroids are chemically differentiated, where the metal would go to the center. Well, then if that happens and that asteroid somehow gets hit really hard and broken up into pieces, which life for an asteroid is a tough life. You'll see they get banged around a lot. Then if metal pieces get thrown out, those look like asteroids on their own, just pieces of metal floating in the asteroid belt, and we call those M-type. So what it says is these probably came from an asteroid that was chemically differentiated, then shattered, and the iron core or part of it was ejected by itself. These are often what people find with metal detectors. You can go hunt for meteorites or pieces of asteroids, if you want to call them that, with a metal detector. And you can just wave the metal detector around and you'll find people do it regularly, and you can look anywhere on Earth and because they can fall anywhere. In fact, there are robotic vehicles running around in like Antarctica looking for any rocks at all, because if there's a rock laying on top of the ice in Antarctica, it almost certainly got there by falling from the sky. And so most rocks that are laying on the surface out there on the ice are meteorites, and so you can collect them. That's one way to get them. So this is just a chart. The x-axis here, the horizontal axis, is the distance from the sun. And then the vertical axis is percent of the total. That's what type of meteorite. And so you can see the S-types peak closer to the sun, and the C-types peak farther from the sun. Really what this is saying is that silicon-based rocks can form at a higher temperature, where it's warmer, than carbon-based rocks. And so these carbon-based rocks were more easily forming farther away, and so that's why you see they're more common in the outer range of the asteroid belt than in the inner range of the asteroid belt. And the M's, of course, just fall in the region where they both are, because they come from either one or the other if they had an iron core or metal core. The first 3 asteroids photographed from spacecraft flybys, printed on the same scale. This is Gaspra and Ida. The 2 on the right are S-type, taken by the Galileo spacecraft. Matilda is a C-type and was a flyby of the NEAR Shoemaker aircraft. NEAR stands for Near Earth Asteroid Rendezvous Project. So there have been a bunch of projects to look at asteroids. There is even talk of mining asteroids because they can have some valuable metals in them that are uncommon on the surface of the Earth. And so there's been discussion of that. We'll talk about more of those as we go. Ida in that picture is about 50 kilometers. Dactyl is another one. It's not in there. It's about 1.5 kilometers. Mars has 2 moons, Phobos and Deimos, that are about 15 miles and 8 miles in diameter. Both are probably captured asteroids. That's a really rare thing. The physics of capturing an asteroid is very difficult. I talked a little bit about that when we were talking about the moon and capturing a moon. But there are lots of asteroids, and occasionally it happens The Jovian planets, Saturn and Jupiter, each have 60 moons, and probably some of those are captured asteroids. These are quite small and look like asteroids. They're rocky. We'll look at a picture of them here in a second. The Near-Earth Asteroid Rendezvous Near spacecraft Shoemaker went into orbit around Eros in S-type for a year, studying its surface and composition. At the end, the mission landed on Eros and sent data for another week. Most asteroids are bags of gravel. Eros, it appears, is pretty solid. So planetary defense. So we've had some fairly serious asteroid events in our history. As recently as 2013, in Chelyabinsk, in Russia, there was a 20-meter asteroid that was 500 kilotons and 30 times larger in energy than the nuclear bombs of World War II. So if we hit a city with one of those, it would be pretty bad. Fortunately, the chances of that are really small. In 1994, a 1 kilometer object, so that Chelyabinsk was 20 meters, this is 1,000 meters, passed between the Earth and the Moon. So these are things we want to kind of watch. In 1908, in Tunguska, in Russia, a 40-meter asteroid wiped out a forest as large as a city. NASA has a project called Space Guard that wants to account for 90% of NEOs, near-Earth objects, greater than 1,000 meters in diameter. We now have about 1,000 of these. Estimates of 1 million near-Earth asteroids smaller than 1 kilometer but capable of wiping out a city exist. So these are the things we probably want to watch because they have the capability of doing some harm. There are two best approaches. There are two sort of discussed approaches. There might be better approaches. One is just to deflect the asteroid or comet, by the way, either one really, is to find them when they're very far away, and then push on them very gently for a long time. You just want them to miss the Earth, and so if you get them when they're really far away, you can just push on them a little bit for a long time, and that'll get them to miss the Earth. The other one is more aggressive. It's where you try to break the asteroid into small pieces so that even if they hit the Earth, they burn up mostly in the atmosphere. So those are the approaches that get discussed, although none is close to being implemented at this point. These are Mars's moons. It's just a picture of Mars's moons. You can see these guys have pockmarks all over them. They've been hit a bunch of times. A is Phobos, which is the larger one, and B is Deimos. They were discovered in 1877 by an American astronomer. Here's another asteroid, Itokawa. It appears to have no craters on it, which means it's probably more gravelly, than some of the others. And it kind of looks gravelly. This was taken by the Japanese Space Organization. Here's an up close of an asteroid. The near-Earth asteroid Bennu was imaged by the OSIRIS-REx spacecraft in 2020. Bennu is a small, half-kilometer diameter, rapidly spinning dark asteroid. Its low density suggests it's loosely bound rubble. Here, this vehicle has landed on it, and it's taking a sample that's going to be sent back to the Earth. About 100 grams of surface rock and dust will be returned to Earth by 2023. This is a return, right? This is landing on the thing and then returning something to Earth. This is the toughest mission to do. Everything has to work for you to get this stuff back. If you're interested in NEOs or NEAs, this is an interesting graph. The horizontal axis is the discovery date, and the vertical axis is the cumulative number of objects we have found. Notice this red curve is greater than 1 kilometer in size. The yellow curve is greater than 140 meters in size, capable of wiping out a city. And then the blue is all sizes that we've found. And so you can see the good news is we seem to have tailed off in finding new objects that are bigger than a kilometer in diameter. Right, the top of this red one is becoming pretty horizontal, which means it's not changing much. But the over 140 meters, we're still accumulating a lot of those. We just need more spacecraft looking. And finally, all sizes are still rapidly increasing. Hopefully, we'll get a better picture of this over time, and be able to track them. If you can track them, you can kind of predict where they're going to go and where they'll go even 100 years from now. And so if we have one that in an orbit that might hit us in 100 years, we could just make a small change to its orbit now or soon and make it miss us. They're really good at tracking the orbit of these guys for long periods of time, predicting them into the future. That was all the kinematics we did at the start of the summer. This is a picture of the Chelyabinsk meteor that passed across the sky. What was interesting about it, and you should Google it, was lots of dash cams had footage of it. And so there's lots of video of it from different angles and different things that it did. The Tunguska was happening when there was some upheaval. And so nobody got in there to look for maybe 5 or 10 years or something like that. And still when they got there, this forest was completely devastated. Finally, there's a big event that wiped out the dinosaurs. This is about 65 million years ago. This was a 6-mile asteroid that hit off the Yucatan Peninsula in Mexico. Produced enormous tsunamis, enormous heat, months of dust in the skies blocking out the sun, wiped out 75% of species. The discovery of this was really interesting, how these guys figured this out. But what they had found was a global layer of iridium at a certain geologic time. And they were trying to figure out what that was. And it ended up that it happened, this global layer of iridium was deposited on the planet about 65 million years ago. Iridium is a metal that's commonly found in asteroids, but not very common on Earth's surface. And yet it was all distributed all over the globe at the same time. And so eventually a guy named Alvarez sort of put all the pieces together, and they found the crater, which was in the Yucatan Peninsula, and they looked at that crater and found minerals at the bottom of it that only get created in enormous heat. So over the last probably 40 years, all of those sort of pieces have been put together. They're still learning a lot of stuff about it, but it's pretty well understood at this point. Okay, let's talk comets. So comets are mostly icy objects with some rock from the outer solar system, typically beyond Neptune's orbit. They're often called trans-Neptunian objects. Comets that enter the inner solar system that we see typically start out as an icy rock a mile or two across. This is called a nucleus. So these objects are in the outer solar system, and they're just icy rocks out there, the way asteroids are rocks in the inner solar system. However, when these objects come in, when these comets come in from out there, they get heated up by the sun as they get close to it, and all this icy rock they have starts to evaporate. And with it comes, they get surrounded by gas and dust. And so they develop what we call a coma. That's the ball of gas that surrounds the nucleus. The nucleus is just a hard core that you started with a mile or two across. It develops this coma around it, which is just a fuzzy ball of gas and dust surrounding the comet. It can get to be 1 million miles or more in diameter, this coma. Now remember, you're just starting out with a mile or two of ice and rock, but it can expand out into a very diffuse ball, and we'll see pictures of them. So hang on a second. So these are the parts of a comet, right? Here's the coma that we're talking about, right? This comet, say, is moving down and to the left. You can see the little arrow, and the sun is in the straight down direction. So the sunlight and the sun's solar wind that we talked about before both act on the coma, right? And so it turns out the solar wind, both of the solar wind which pushes away, interacts strongly with these gas atoms and ions that are in the coma. And so they give you a very straight tail, the solar wind does, we call the ion tail, pointing straight away from the sun. No matter which way the comet's going, the ion tail points away from the sun. The dust tail and the gas tail, those particles are a lot bigger. They don't interact well that much with the solar wind, but they do get pushed on by the sunlight. The radiation pushes on them gently. And so that tends to push them away from the sun also. So typically you get two tails. One is a straight one, we call the ion tail, and one is curved, mostly away from the sun, and that's the dust tail. You're getting some sizes here, right? This is 1 to 10 kilometers. A typical size for the coma is maybe a few 100,000 miles or 1 million miles or something like that. There's a wide range. These tails can be tens of millions or hundreds of millions of miles long. It just depends on how big the comet is and how close it gets to the sun. This is a typical comet orbit, right? The orientation of a typical comet changes as the comet passes perihelion. And so you can see it's the tail, you can tell, is always pointing away from the sun. You might think it would be pointing opposite direction the comet's going, but there's no air in space. And so there's nothing to, like when you run and your hair blows behind you, that's because you're running through the wind. There's nothing to run through in space. And so the tail can be in front or behind. And it's always just pointing away from the sun, or generally away from the sun. So pressure from sunlight and solar wind create the tail, to create the two tails. The ion tail interacts strongly with the solar wind and points in a straight line away from the sun. The dust tail is pressed on by radiation and pushed off the comet in a direction generally away from the sun. Dust particles are small, which we'll see in a minute, but still much more massive than ions, which are individual atoms and molecules. So dust particles, they interact less strongly with solar radiation than ions do with the solar winds. So the dust tails just make a curved path pointing generally away. Comet tails can be 100 million miles or longer. These are just 3 images of Halley's Comet. Stacked on top of each other. You can see these stars in the background are blue, red, and green, and they're just images stacked on. The comet moved between the pictures, but it's how you get a color image of a comet. It's how these comets. Sometimes you can't see the two tails. Maybe I see a tail going this way and a tail going that way. It's hard to tell, and it depends what angle you're looking from. Here's another picture of Halley's Comet. Did I miss something there? No, I didn't. This is a close-up. It's from a distance of about 1,000 kilometers, so 500 miles or something like that. The last time Halley's Comet came through was in 1986, and some friends and I went out to see it, and it was very disappointing. We had a little telescope, and you could see a faint smudge just above the horizon on this particular night. We were south of Norman, Oklahoma. It was very disappointing, but it wasn't anywhere near as nice as Hale-Bopp that I was describing at the top of this section. But it was still cool to have seen it. The next time it comes is in 2061 or something like that. I will not be here. This is Edmund Halley. He was the one who figured out the comet, and so he just noticed that this comet was coming back every 75 or 76 years and decided that it was an object that was just orbiting the sun just as the planets do. He was a contemporary of and friends with Isaac Newton, and so he consulted with Isaac Newton on this little project and encouraged Isaac Newton to solve the gravity problem. And he contributed to some other interesting projects. One was determining the distance from the Earth to the sun, which hadn't been done yet. He suggested some clever ways to do that. He was a talented mathematician and physicist. So here's a piece of captured dust. This particle is seen through a microscope. and it measures 10 microns or 1/100th of a millimeter. Right, so go look at what a millimeter is and then divide that by 100, and you'll see that's really tiny. However, keep in mind that it's still 100,000 times larger in diameter than a single atom. And so when sunlight is pushing on these things, it has a much larger load to move than the ions do interacting with the solar wind. So there's a typical dust particle. This was found in the upper atmosphere of the Earth. We often find things that can be determined to be from something else. These are just two comets that are approaching the sun. On the left again is Hale-Bopp, which is spectacularly fun to look at. Most of the time there's a comet you can see if you have a fairly high-powered telescope, and most of the time they just look like a faint fuzzy ball. You rarely get images like this unless you have a really high-powered telescope, except, like I said, with Hale-Bopp, everybody got to see Hale-Bopp. So here's a comet that was approaching Jupiter. This is what we don't want to happen to Earth. Right? This comet was seen probably a year in advance, and the guys who were studying it, Shoemaker and Levy and others, figured out that it was going to hit Jupiter fairly early on. These guys are really good at predicting the trajectory of these comets, and they decided this was going to hit Jupiter. And so we did, almost exactly when they said it would. It happened the weekend of my wedding in 1994. And so some of my friends bought little telescopes, and we could see little spots where these guys had hit Jupiter. It made the gravity from Jupiter kind of tore created tidal forces that kind of tore the comet apart eventually and broke it into a whole bunch of pieces. And so pieces hit at different times. And then you could see the scar. Here's a scar, for example. You can see that little mark on the quote surface, unquote, just the upper atmosphere of Jupiter. We got to see those. So where are comets? We have an asteroid belt for asteroids. And so there are some regions for comets. The Kuiper belt is kind of like the asteroid belt, but beyond Neptune. If you look at this picture, so this axis here is in astronomical units, and 10 astronomical units is here, and that's where roughly Saturn would be. Notice that this is a log scale, though, because over here is 100, and over here is 1,000. So you might think twice as far would be 20, but actually on this scale, 20 is about here. And so, Neptune is about here where the cursor is right now. And the Kuiper belt runs from about there up to, just depending on how you count it, sometimes they just say up to about 50, but maybe beyond that, in the plane of the solar system. So in the disk that's the solar system is where the Kuiper belt is. And the objects in there are called Kuiper belt objects. Even though they're comets, we also call them Kuiper belt objects. Also, further beyond that is this thing called the Oort cloud. And the Oort cloud is a spherical ball of debris, mostly icy, that exists around the sun at enormous distances. And so Kuiper belt objects produce what we call short period comets, and the Oort cloud produces long period comets. And so let's just go through these again. Comets are typically found in the Kuiper belt and the Oort cloud. The Kuiper belt is named for Gerard Kuiper, a Dutch guy who lived from 1905 to 1973, who postulated the existence of an asteroid belt for comets beyond Neptune. The Kuiper belt extends, depending on who you ask, it's beyond Neptune. The thick of it, you saw how the asteroid belt looked, right? The thick of the Kuiper belt is between 30 and 55 astronomical units. The Oort cloud is also named for a Dutch astronomer, but this guy's named Jan Oort, and he was born in 1900 and died in 1992. And he also postulated the existence of this cloud based on how both of these guys sort of made these conclusions based on how we thought the solar system formed. They thought there ought to be more icy objects just laying around out there, and they predicted where they would be, and we found them. Rather than a disk, the Oort cloud is a spherical distribution, as you saw in the last figure, of comets extremely distant from the sun, but still orbiting. the Oort cloud ranges from about, that should say 2,000 astronomical units to possibly 100,000, or roughly a light year. The Oort cloud can contain as many as trillions of comets, accounting for maybe 2% of the total mass. Remember, we said the sun is about 99.8% of the mass of the solar system, depending on how you count the comets. If you count this Oort cloud extending out to a light year from the sun, then you can get as much as 2% of the mass of the solar system in comets. But that's way, 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 way more than the total mass of the planets and stuff like that, and that stuff is extended way out. So if you look at comets that enter the inner solar system, they get degraded over time. We've sort of seen how that happens. The sun shines on them, it pushes a tail off of them. They get an ion tail and a gas tail. They get a coma, and a typical comet, that's a mile or so in diameter, might last 200 orbits before it's finally all its debris it's just been turned into gas and dust by the sun each time it comes in. After this time, the comet's path, that ellipse that it follows, is just strewn with gas and dust, and there's no main comet anymore. If this happens, or when this happens, if the Earth happens to cross its path in the course of the Earth's orbit, then we get a meteor shower. This is like you'll hear the Leonids or the Perseids, these meteor showers. What it is the Earth passing through the trail of a dead comet. And so sometimes that happens, that'll happen several times a year. And as we pass through this debris that's still orbiting the same path it was orbiting when the comet was whole, is now just a bunch of debris that gives us a meteor shower at night. So I have questions here. Check the online version for a more developed question list. I'll probably add a few more questions.